Okay, today we're going to consider the atmosphere, and particularly we're going to look at the role of ozone in the atmosphere. So first of all, we need to think about what the atmosphere consists of. And if you think of this as just a part of the Earth, then what you need to know as ESS students is that the first layer of the atmosphere is called the troposphere. And in that we've got all our weather, okay, and living systems. Okay, that's where a lot of the interesting things happen that we need to know about. And then the next layer above the troposphere is the stratosphere. And this doesn't have so much to do with the living systems directly, but it's really, really important because it contains ozone. And ozone is a molecule that contains 3 atoms of oxygen. Okay, so this is where we're really concerned about what's happening in the atmosphere. There are other layers above the stratosphere, but you wouldn't be expected to know these. You do need to know what the atmosphere contains, and most of the atmosphere, something like 78% of the atmosphere, is made up of nitrogen gas, and this is very unreactive, let's say unreactive. The fancy science word for that is inert. Okay, and so that links to what happens with the nitrogen cycle, because organisms have to convert that nitrogen gas, microbial organisms, so that other organisms can make use of it. Okay, so about 20% of the Earth's atmosphere is oxygen. Okay, and that again is another molecule with 2 atoms in it, O2. So what we've got left is, actually we're going to make it easy for ourselves, and we're just going to change that to a 9. It's around 78-79%. Okay, so we've got 1% left, and in that 1% we've got all the other gases that we need to know about. So we've got carbon dioxide, we've got water vapor, we've got things like argon, and other very low abundance gases. Carbon dioxide, for the vast majority of the human history, it was at a point of 350 parts per million. So that's 0.035%. But at the moment we've gone over 400. We're at 408 about at the moment, but we'll say ppm, parts per million. So 0.04% of the Earth's atmosphere is carbon dioxide, and we know that this has an inordinately large, a really big effect on our atmospheric system. But anyway, today we're going to concentrate on what's happening here with this ozone. So we need to, this ozone in the stratosphere, I like to call it good ozone, because it protects us it protects us from ultraviolet light, UV light. Okay, so it's really, really important. If we don't have this ozone, then we get problems like skin cancer, because ultraviolet light has a very high energy, so it causes mutations in DNA, in cells of DNA, and obviously our skin cells are the first barrier to protect us. It can cause cataracts in eyes. Cataracts. Okay. And in plants, it can affect productivity. Particularly, one of the most important areas is marine productivity. Phytoplankton seem to be particularly vulnerable to high levels of ultraviolet light. Okay, so that's why stratospheric ozone is really important. But how does it get there? So we know we have oxygen. Oxygen is this double atom of oxygen. And what happens is that ultraviolet light actually splits apart the oxygen until we have separate atoms of oxygen. But oxygen isn't meant to be separated like that. It's not very stable. And so what happens is that when the oxygen atom meets another oxygen molecule, it forms ozone, O3. And then the reason that the ozone protects us is that we've got these triple atoms of oxygen, and the ultraviolet light also can split those apart, and so you get the oxygen formed again, and you get an oxygen atom, and it goes round in a circle. It's called a cyclical reaction. So the oxygen atoms get broken apart, they bump into other atoms, and they reform. And this is the role of ozone in protecting the Earth. It's not intentional, but that's the consequence of it. So ozone protecting the Earth from ultraviolet light. But guess what humans did? They were so smart, technologically innovative, and they created chemicals which ended up being what we call ozone depleting substances. ODSs. And these are largely what we call halo alkanes. So the halo means that they contain chlorine. I should write this out for you. Chlorine. They contain fluorine and other atoms from that group 7 of the periodic table, so bromine, iodine, etc. Okay? The most famous of these, and the first one to be discovered to have this unfortunate property, was substances called CFCs: chloro, fluoro, so that word, the alkanes, is the carbon part of the name there. And unfortunately, what these gases, they're very unreactive actually down at the Earth's surface, and they thought this was great. They're really useful, and they were used for things like sprays, so propellants in gas. So that means that in spray cans, that's the word. And so what happened was that in these spray cans, you press they contain a gas, and when you press down the nozzle here, the gas propels the substance you're actually wanting to use out of the can. So when I was growing up, this would be things like deodorant sprays, okay? But they were also really useful in air conditioning systems. Air conditioning systems. And in fire extinguishers, in one type of fire extinguishers. They were used as refrigerants, so in fridges, in freezers, things like that. They've even been found to be used in pesticides and soil conditioners, but I'm not sure what the chemistry of those molecules, but that's where they're found. Okay, so what happened was that all these sprays were being let off at the Earth's surface, and then they were travelling up to the stratosphere, and at the stratosphere they became reactive with the ozone. So what happens is that these molecules, which you can shorten to think of like that they form chlorine or fluorine in the atmosphere, or they're separated as just atoms like that. And when they are floating around in the atmosphere, they act as a catalyst. So for those of you who've done a bit of biology or chemistry, will know that a catalyst speeds up a reaction. Okay, it speeds up a reaction, and it is not affected by that reaction, or in the case of this one, it's actually reforms so that it can be used again many times. And in fact, we think that the lifespan of these molecules is more than 100 years. So what happens is that this chlorine atom comes along and it meets an ozone molecule. This is the ozone here. And if you were answering an exam question on this, it would be fine to draw out sketch diagrams like this. But if you start writing chemical reactions, you do need to be careful, because chemical reactions can be right or wrong. And so for ESS students who maybe don't have that level of chemistry, then it's better to use the words, or you can do these sketch diagrams. So here we go. So the chlorine takes away one of the oxygen atoms from the ozone molecule and forms a new molecule here, the chlorine joined to the oxygen. And so now we've just got oxygen. We've lost ozone. The ozone's been depleted, you could say. It's a nice word to use. And we've got this new molecule here. So what happens is that there are oxygen atoms floating around in the atmosphere. As we know from this reaction up here that we looked at, there's a constant movement between oxygen atoms and ozone. So we've got oxygen atoms in the atmosphere, and that will react with this one to reform the chlorine and to form oxygen again. So this is the catalytic reaction, because we're reforming chlorine, and it can go on and destroy the ozone in a cyclical, again it's another cyclical reaction, but it can do it again and again and again. Okay, so that's really bad for us and the earth. Okay, so that's why these ozone depleting substances are really bad. So unlike the challenges that we've had with trying to tackle global warming, the world actually came together and united to form, to agree upon a treaty, and that was the Montreal Protocol. And this was in, I think it was something like 1987. It was in the 1980s. And what was good about this was that business could see that this needed to be done, and the US was actually a leader in this protocol, and pretty much all countries came together and agreed this Montreal Protocol, which was to phase out these haloalkanes, these CFCs. And they did this by replacing them with other chemicals. And I guess you could call that substitution. Okay, and this was pretty successful. The businesses had the chemistry to do this. But then what they discovered was that although these substitute chemicals were not depleting the ozone anymore, what they were doing was that they were worse at being, and here we're hopefully not going to confuse you, greenhouse gases. So this is where students often get confused, because they confuse ozone depletion with global warming. So ozone depletion, or the loss of ozone, does not cause global warming. But the causes of ozone loss are also greenhouse gases. And so recently there was an addition to the Montreal Protocol that was agreed in Rwanda, in Kigali. And what this did was that it agreed to phase out all these ozone depleting substances that have another effect on greenhouse gases. Okay, and so this was deemed to be very successful. It's probably the most successful environmental agreement that's been developed. So when you come to evaluate this, there are some problems. So the evaluation, there are some problems. That is, there is some black market trade in ozone depleting substances because they're cheaper than the alternative. Okay, but generally it's a very successful agreement, environmental agreement. So let's think about what else you might need to know. So if we go through the pollution management strategies, it's a popular exam type question. Okay, we've got the first one being altering human behaviour. So in the 1980s there was lots of education, campaigns. I was part of letter writing campaigns, and people stopped using spray cans. Of course, it wasn't completely successful. It was only some people doing that. Then you've got the control of the release of the pollutant. And here we've got the international agreements. And then finally, the third stage is about remediation. It's about getting things back to the way they were or improving the environment. And this is only done by, you could say, self-healing. The Earth's systems just recover over time. And there's not much we can do to help that other than to stop the ozone depleting substances in the first place. Okay, so hopefully that helped you a bit with understanding ozone depletion.